There we go. All right, so we're getting ready to start module number 2. So as we look at our module number 2 here, we're gonna look at the learning plan first. And you're going to notice we're going to be focusing on chapters 12 and 16. Not in their entirety. We're picking out parts of 12 and parts of 16. So tonight we're going to focus on the chapter 12 stuff. And then the next time that we get together, we'll be moving on and looking at the balance of this module. And we're going to be doing chapter 16. As we go down here, I have referenced the sections in the textbook that that we'll be, using. And then also the sample problems that we'll be going over, which will be your practice problems that you'll be handing in. And as you know, there's 2 parts to every module. You're going to be handing in practice problems, which are the ones we do here in class. And then you're going to have your application problems. I want to let you know as well, I'm just going to move back a level here. And as we look at the practice problems for module 2, I'd like you to create another equation sheet or continue to add to the one that we had in module 1. I find it so helpful, and I think it's a great place for you to kind of organize your thoughts and equations and concepts on an equation sheet. And I think you're going to find that come in handy as well. So I'll be kind of showing you mine as we go through the lecture and things that I find helpful on it. And because I too reference an equation sheet. I mean, and I actually make mine up new every single time that I, teach a section. So when I do this next year, I'll do the very same thing. I just find it so helpful to go through there. And again, it kind of organizes things and it helps me remember things a little bit better too. So I'm encouraging you to do that. And then the sample problems will be the things that you hand in for the practice problems, just like we did for module 1. So heading back over and going up to our learning plan, let's open up the PowerPoint for chapter 12. Zoom out here a little bit. So as we look here, chapter 12 is really applying Newton's second law. And we know Newton's second law to be the summation of the forces is going to equal mass times acceleration. So if there is a resultant force, so we are in dynamics class now. We're not in statics anymore. If you remember, we used to set the sum of the forces equal 0. Okay, that means that things weren't moving. Okay, now in dynamics, we have it equal to something, and that something is mass times acceleration. Okay, which is Newton's second law. So if there is a resultant force, okay, so when we're moving, there is, okay, acting on a particle is not 0, that particle will have an acceleration proportional to the magnitude of the resultant and in the direction of the resultant, okay? This form of the equation always assumes that we have a constant mass and that mass isn't changing, okay? So again, acceleration is when we have a resultant force, we have a force that's left over here, and now we're actually speeding up and or slowing down. Okay. Now, systems of units. So in this section here, we are going to be looking at 2 different, types of units and problems that we encounter. So we're going to have what we call SI units or international system of units. And then we also have our US customary or English units as they're referred to. So depending on what the problem is set up, and we've come across this many, many times, but the one unit that I want to focus on here is the Newton, okay? The Newton is the unit for force in the metric or the SI system, okay? And the Newton expanded out is a kilogram meter per second squared. So these are the actual expanded units, but in honor of Sir Isaac Newton, that unit is called the Newton, okay? So whenever you are, in a problem, if you need to do a cancellation of units, and as you know, you guys are getting a pass on that in this class because you've got plenty of that. But if you ever want to check, just to be sure, you would have to expand out that Newton to see that. And the reason that the units are the way they are is because when we calculate, for instance, weight, we're going to take the mass of that object times the rate of acceleration of gravity, okay? And so kilogram meters per second is what that unit of force is going to be, okay? Now, when we go down here to US customary units, okay, we use pound mass or pound force, okay? Now, when we look at mass, the mass of an item in the English system is called a slug. I think we talked about that last week. And a slug expanded out is going to be a pound divided by the rate of gravity, okay? And so because the rate of gravity in the English system is feet per second squared, this per second squared multiplies on top. So the expanded units for a slug or for mass in US customary is pound second squared per foot. Okay, so so we'll see that. I think we're going to be doing one of our example problems tonight is going to be using the English system, which I think is our very first example. So so we'll kind of see this as we go along. Now, equations of motion. So as we know, Newton's second law says the summation of the forces is going to be equal to mass times acceleration. So the left-hand side here is kind of like, if you would, our statics problem, or sometimes referred to as the kinematics. It's the reference to, you know, how things like external forces that are going on. On the right-hand side, we have our kinetics, and that is going to be like the inertia that occurs. So if you remember back from physics, mass is the measurement of inertia, and inertia is always going to be a resistance to a change in motion. So if something is already in motion, it's like it wants to stay in motion unless there's an external force acting on it. So things like gravity or air resistance are going to, you know, change that state of motion, or an external force that, you know, pushes or pulls or something on it. So so as we look here, you'll notice that when we are in 3D space, we have some of the forces in the X is going to be equal to the mass times the acceleration in that same direction, or the X direction, and then so forth for the Y and also for the Z. So we'll see that when we look at our problems, we have to kind of know like what axis that we're on, and we'll see that in the examples that we look at. So free body diagrams and kinetic diagrams. Free body diagram is going to be our statics that we are so familiar with and are very good at. So, you know, looking at this block that's on an inclined surface being pulled by a force here, a string that's attached to it, we're going to put all of the forces that are acting on that body, including the weight. The weight is the mass times the gravity, or the acceleration of gravity. So you could very well, if you knew what the weight actually was in newtons or pounds, you would show that as a force going down straight to the center of the earth, if you would. Then we've got a friction force here that is going to oppose motion. So it's going to, if you would, go in the opposite direction of the way that we expect this to be moving. Because this is a cable that is pulling in this direction over that pulley immediately attached to that block, you're going to notice that we have that 225 Newton force, and that's that pulling force. The friction force is going in the opposite direction because it's going to be moving, you know, up and to the left. So that friction force is going down and to the right. And then lastly, we have a support force, or what we call the normal force. The normal force is going to be perpendicular to the surface that this block is riding on. Okay, so you'll notice that it is at a 90-degree angle to that surface. This is statics. Okay, so we're going to be, you know, drawing the body, if you would, freeing it, and then, you know, putting all the forces that are affecting, you know, what's going on. Okay. So that's going to be the static side of things. The kinetic side of things is going to be over here. This is going to be where we start looking at what we call the inertia, or the inertia terms that we have. So what I like about this is on the left-hand side, okay, this is going to be our sum of the forces, our statics, is going to be equal to the kinetics side, or maybe you want to even call it the physics side of things, is going to be equal to what's happening with that mass and acceleration. So, so then we put those forces on there. So, so you're going to see this play out as we do our examples. We'll do a lot of application of this. So our first example that we're going to be looking at is sample problem 12.1. And what I'm going to do is I'm going to pull out what you'll see in the textbook as the problem statement. So I'm going to open that up and put it underneath here. And I'll zoom in so we can get a good look at this. I'll kind of tip it up so that it's, maybe we don't have the glare on here. But basically what we have, it says we have a 200-pound block, and it's this illustration over on the left-hand side. It rests on a horizontal plane. We want to find the magnitude of P that's coming in at that 30-degree angle on that upper left-hand corner. We want to know what that force P is required, what force of P, I'm sorry, what the magnitude of the force P is required to give that block an acceleration of 10 feet per second squared so that it's moving to the right, okay? They're telling us that the coefficient of kinetic friction between the block and the plane is 0.25. Now, if you recall, there are two states of friction. There is static friction and there is kinetic friction. Kinetic friction just means that this is when it is moving. And as we know, that changes a little bit. So, there's always going to be two values for two values of friction, static and kinetic, for any two surfaces that are together. All right, so let's first identify what we know and what we need to find. So this is sample problem 12.1. Okay. Now, because we are going to be dealing with directions of forces and such, we're going to be putting our convention in the upper right-hand corner. We're not dealing with moments, so we don't have to add that here, but just like we did for statics, we want to put our convention up there so we know why we identify, you know, certain things positive and negative. We need to, I'm not going to put all the, I'll put all the givens. It's the right thing to do. We know that mu, or the kinetic coefficient of friction, is 0.25. We also know that the weight of the block, I'm going to put WT for weight, is 200 pounds. So we're in the English system. We also know that the acceleration that we need to achieve is 10 feet per second squared. And we want to find, P, okay? So that it can accomplish that 10 meters or 10 feet per second squared, okay? So let's draw our block, and we're going to draw it in terms of, so I'm going to start on the left-hand side here with like our statics diagram, and then we're going to set it equal to our kinetic diagram, or the one that has what we call the inertia terms in it, okay? So over on the left-hand side here, we're going to show the block with any and all forces that are acting on it. So here's our block. We know that center of gravity, we're going to have 200 pounds acting down, okay? We know that there's going to be a normal force because this is on flat surface, okay, horizontal surface. So that means the normal force is going to be perpendicular to the surface that this block is riding on. We also know that up in that upper left-hand corner, here is force P, okay? And it is acting at a 30-degree angle, okay? Now, it also tells us that that coefficient of friction is acting. So that means that we're taking into account a friction force, okay? That friction force is going to impede motion. So we know that this is going to be accelerating to the right, as it told us in the problem, and actually the 10 feet per second to the right. Okay, so we know that it's going to be going in that direction. So that means that our friction force, I'm going to call it FF, our friction force needs to go in the opposite direction, okay? Now, we're going to say equal to, and now we're going to redraw the same block, but now we're only going to add anything that has to do with the inertia things, so the mass and the acceleration. So we are going to say that mass times acceleration is going to be going over to the right, okay? Now, underneath, I'm going to kind of write that same format that they had before. So this is sum of the forces in the x direction is equal to mass times acceleration, okay? Now, we're only really, in this case, interested in what's going on horizontally because that's where the movement or the motion is occurring. If we look some of the forces in the y, which we will, we don't have any movement in the y direction, so we wouldn't set it equal to that inertia side of things, or that kinetic diagram. We will do some of the forces in the y to get some information here, but we won't be setting it equal to a mass and acceleration. That is reserved for where the movement is occurring, and the movement is horizontal. Okay. All right, so the next thing we need to do is you're going to notice that we have a force that's at an angle. So just like we did in statics, because it's on the static side, we are going to be breaking this into its x and y components. So we're going to have a px and we're going to have a py. Okay. Now, the next thing that we're going to do is we're going to calculate what the mass of this block is. We know what the weight is, okay? But we're going to need it for this side over here. And because we have the weight, we can automatically calculate what the mass is. So step number 1 is going to be calculating mass of that block, okay? So to do that, we know that weight is equal to mass times gravity, right? So rearranging that, we can say mass is equal to the weight of that block divided by gravity, okay? Now, I didn't put it in the givens, but because this is an English problem, our gravity is going to be 32.2 feet per second squared. So we can say 200 feet, I'm sorry, no, 200 feet, it's 200 pounds. 200 pounds divided by 32.2 feet per second squared. Okay. So our mass, if we divide 200 by 32.2, you should get 6.21 pounds times second squared divided by feet, because these seconds squared are going to multiply on top. So this is the mass of our block. Okay, so that means that we now have calculated what the mass is, we know what the acceleration is, so we know some of those terms. Okay. Now the next thing we want to do is let's look at summing our forces in the x and see where we're at. Okay, so if I sum my forces in the x direction equal to ma, let's see what we know here in this equation. So we're going to look on the left, we're going to look on the left-hand side here, okay? And we're going to look at the forces that are in the x direction, okay? So we know that we've got a px. Now, according to our convention up here, according to our convention, we know that going to the right is positive. So our px is going to the right. So this is going to be a positive px because it's going to the right. And then the other force that we have is the friction force, and that's going back to the left. So that's going to be a negative ff. Okay. Now, because we are not in the y direction, we're not summing our forces in the y right now. Okay, we might need to. Then we're going to set this equal to our mass, which is 6.21. Again, we're not going to worry about units because we know that they're consistent with everything. So we'll magically let them appear. And then we're going to multiply this by 10 feet per second squared is going to be the acceleration it told us that we needed to maintain. Okay. So right now, as we look here, we have px unknown, and then we also have the friction force unknown. Now, friction force, how do we calculate a friction force? So if we look here, to calculate a friction force, that's going to be equal to mu, kinetic, the kinetic coefficient of friction, times the normal force, okay? So when we look up here, do we know what the normal force is? We do not. If there wasn't that force P, I'm going to open up the chat. Oopsie. I need to do that. I just wanted to open up the chat box. There we go. Sorry. Maybe I can't. Okay, that's okay. All right. So when I look at my normal force here, we have that Py going down. So the normal force is actually going to be the Py plus the 200 newtons. So those two are going to equal what that normal force is. And we don't know what P is, so we don't know what Py is. But what we can do is we can, I'm going to kind of go down here, sum our forces in the y direction are going to be equal to 0 because we don't have that mass, we don't have movement on the right-hand side here. So we're going to have a positive N normal force minus 200 pounds minus PY, okay? And that's going to be equal to 0. Now, you'll notice that we have PY and PX. And as I said earlier, we're going to need to break those into X and Y components, but we're going to put it in terms of the hypotenuse or P. So let's do that right now so that we can kind of expand this out and write our PX and our PY in terms of P. So I'm going to do that on the next page here. These are going to be the components of P. So if we look back over here, not going to redraw it, you'll notice that we have our 30 degrees here. So for our X component, it is going to be the cosine of 30 times the hypotenuse or P. So our PX is going to be equal to cosine of 30 times P. Now the cosine of 30 is equal to 0.866. Okay, that's the decimal equivalent. So this is going to be 0.866p. So we'll just kind of put a line underneath there and we'll, use it where we need to use it. And then we'll do the very same thing, but this time for PY, we look back at our illustration, it is going to be the sine of 30 degrees. So it would be the side opposite, right? So this is going to equal the sine of 30 times P, which is 0.5 times P. So PY is equal to 0.5 times P. Okay. So now we can do is we can substitute that value here for PY. And I'm going to say, all right, N minus 200 pounds minus 0.5P. Equal to 0. And then solving for N, or that normal force, I'm going to move my 200 and my 0.5 to the other side. I'm going to say N is equal to 200. And if you want to put the pounds in, you can. I really didn't mean to, so I'm going to turn them off now, if you would. Minus 0.5, I'm sorry, plus 0.5P is going to be equal to what the normal force is. Now, we can't solve for that value, but up here, we can insert it for what N is equal to. So we can say that that friction force, I'll put a little line here, we're going to scooch it in, is going to be 0.25 times what N is equal to, 200 plus 0.5P. Okay, so our friction force, again, is not going to have an actual value yet, but we're going to put it in terms of P, is going to be 50 plus 0.125 P. Okay. Now, this value that we have for friction force, not value, but this expression that we have for friction force is what we're going to be putting up there. Okay. And then our component in terms of P for the X is what we're going to be putting here. Okay. So questions so far before I add this? Everybody kind of follow what I was doing as we went along here with the math? All right. Okay. So then I'm going to put that value for P in there, or PX, so 0.866P minus, I'm actually going to go over here a little bit further. Make sure I get it in here, 0.866P. And then this is going to be minus the friction force. So that means when I put my 50 plus 0.125, it's going to be 50 plus 0.125P. The negative is out front, so we'll have to distribute that, is equal to 6.21 times 10 is 62.1. Okay. Now, this is a good thing because notice we only have one unknown. So it looks like we'll be able to solve this for P, doesn't it? Okay. So now what we're going to do is I'm going to distribute that negative. So I'm just going to rewrite the 0.866P minus 50 minus, because remember there's like an imaginary 1 out here, 0.125p is equal to 62.1. And now I'm going to combine my two p's and I'm going to move the 50 to the other side. Since it's negative here, it's going to be added on the other side. So that means I'm going to have 0.741p is equal to 112.1. I'll let you guys catch up. I want to make sure you see what I did. So I took the 50 and I added it to both sides. That's where I got the 112.1. And then I subtracted 0.125 from the 0.866 and I got 0.741. And that had the p in back of it. So my p, solving for that, so I'm going to divide both sides by 0.741. P is equal to 151.3 pounds. Right. So to maintain that 10 feet per second squared, I need to push on my block at that 30-degree angle with 151.3 pounds. Okay. So that is sample 12.1. Any questions on that particular sample problem? This is our first, if you would, practice problem set. All right, I'm not seeing anything, so we'll continue on. I'm gonna go back and kind of catch ourselves up. There are a couple slides where it goes through that same process, but I like writing it all out rather than pointing at a slide. Okay, our next problem, we'll kind of look at it here first. Maybe it's a little easier to look at the problem statement. We have two blocks here and they're connected by the pulley system that you see, okay? Now, in this case, pull out the paper as well. Just trying to get my stuff organized here. So in this case, we have a 100-kilogram block A, 300-kilogram block B. And what we want to do is we want to determine what is the acceleration of each one of the blocks and what the tension in the cord is. So we have a cord that is we're going to say the long cord that goes around here. Okay, we're going to call that tension 1. And then tension 2, there's also a little cord that is going to attach the 300-kilogram block to the actual pulley here. Okay, so we've got that going on. So T1 and T2. And then the acceleration of block A and block B are what we're going to be, trying to find for this problem. So our strategy here basically is going to be looking at block A by itself, block B by itself, and the pulley by itself. And then as we go through that process and set our, statics diagram equal to our kinetic diagram, we'll be able to kind of work through this with, with the information that we have. So I am going to go underneath my camera and we are going to start just like we did before. Identify the sample problem that we're working on. And this is 12.3 this time. Okay. I'm going to put my convention in the upper right-hand corner. And I want to find acceleration of block A and the acceleration of block B. And also, as I said, I'm calling it tension 1 is going to be for the long cord. And T2 is going to be the pulley to block B cord. Okay, it's going to be like the little short one. And then they also mention in the problem statement that the surfaces that they're riding on are frictionless. So we don't have any coefficients of friction or friction forces to account for here, okay? All right, so let's start by looking at block A. Block A. So block A, and I'll kind of go back and forth maybe here. So block A is sitting up on that table. And it's got the attachment to the cord that then goes down, and is attached to, if you would, block B. So we're going to look at this block right here. Okay. So I'm going to draw block A. And I'm going to draw this one over on the left-hand side. So don't put it in the middle because we're going to do the, some of the forces here is equal to the mass and the acceleration over here. So we want to kind of keep this on the left-hand side of your paper. Now, the forces that are acting on here, the weight, right? The weight of block A is going to be going down towards the center of the earth. There's going to be a normal force on that block as well. We know that this block is 100 kilograms. Okay, so I'm just putting that on there. And then we also know that there is a string, and we're going to call that tension 1. It's going to be the tension in the cord or the string that is attached to block A that is then, heading down to block B. Okay, so this is the static side. This is going to be the sum of the forces. We're going to go in the X. Now, in this case, the block is moving in a horizontal direction. Okay, so technically, the Y's aren't really of concern to us, all right? Because they're not going to play a part in the mass and the acceleration side of things because we're trying to find the acceleration and the tension in the cord, right? So this is going to be equal to, we're going to redraw that block, okay? And we know that it's a 100 kilogram block again, and that the mass and acceleration of that block are going to head to the right in the direction of motion, okay? So over on this side, this is going to be mass of block A. I really should put the mass A there because there are two different masses, times the acceleration of block A. Okay. Now, as we look here, then we want to, find out what is the summation of the forces in the X direction on the left-hand side here. And we only have one force in the X direction. It is going positive, and that is T1. So that's the tension in the cord. That's attached to block A here. It's going to be equal to, we know what the mass is. We know that it's 100 kilograms, right? So we're simply going to put 100 in front of here. And acceleration at A is one of the things we're trying to find. So we're going to put this in terms of the acceleration of A. All right. And we're going to let this sit. Okay. This is as far as we can go with that equation because there's two unknowns. All right. Now what we're going to do is we're going to look at block B. So I'm going to do my little wavy line. And I'm going to do block B. Okay. So let's go back to the illustration. Block B is hanging right here. All right. So it's still in kind of that same orientation, but now it has on the top of it, it has attached to it that cord going to the pulley that's holding it up, if you would. Okay. So let's draw the statics diagram, if you would, of our block B. So we're going to show block B like this. Okay. We know that it is 300 kilograms, but force-wise, we're going to want to put the weight of B going down. Now, this is not sitting on a surface, so there isn't a normal force, but there is the tension in that little section going from block B to the pulley. That's the other tension that we want to calculate. That's tension 2. Okay. So those are just two forces in the Y direction. Now we're going to be looking at this, some of the forces in the Y, because that's the direction in this case. We look back, that's the direction of the motion of B. Horizontally, A was moving, but because we're going over that pulley, vertically, B is moving. So it's a new body that we're looking at, okay? So this is going to be the sum of the forces in the Y direction. So equal to, and now we're going to draw the block again. And we are going to be adding in the mass and the acceleration, okay? So now the mass and the acceleration here are going to be going down, okay? And the reason we're going down is because if you remember, A is going to be moving to the right. If A is moving to the right here, then that means B is going down, right? That's its motion. So this is going to the right, this is moving down. Okay, if it was going the opposite direction, then we would show the mass and acceleration going up, okay? So this is mass B times acceleration B. Okay, and we know this to be 300 kilograms. Okay, so we know the mass of B is 300 kilograms. I've got to put a negative in front of it because it's going down. So negative MB AB. Okay. Now, over on the left-hand side, we've got two forces. We've got the weight going down of block B, and we have the tension in that cable going straight up. So we can calculate the weight because we know this is 300 kilograms, right? So we can say WB is equal to mass times gravity. We know gravity in the SI system or in the metric system is 9.81. So we're going to say 300 times 9.81. Our weight of B is going to be 240 newtons. See, I'm sorry, 2,940 newtons. Okay, so this is 2,940 newtons. Okay, so that means we can then write some stuff down below here. So looking at the left-hand side, some of the forces in the Y, we're going to have a positive T2 and a minus 2940. Okay, don't put your newtons in because again, it can get confusing as to what's actually variables and what's units. And then minus the mass 300, okay, times acceleration of B, because we don't know what that is, right? So now we kind of have this as far as we can go because we've got two unknowns. So we really can't go any further with this. So we're just going to kind of let this sit. Okay, I'm going to let that one sit. The next thing we're going to do is we're going to look at the pulley, okay, and what it does. So we're going to draw a free body diagram of our pulley. Okay. So we're going to draw the pulley here. And we know that the tension going down on that pulley is our T2. That's going down to block 2. And then T1 is the value on either side here. Let's look back at that pulley and see how it's attached. So the pulley at C here, that's the center of our pulley. It's going down towards B, so that's our T2. And then it's got two sides that are going up. This is all the same cord, okay? So T1 are the two values going up there. Now, we don't need to know what the size of that is. We just know that because it's a pulley, it's going to be evenly distributed on either side. So we can say some of the forces in the Y here are going to equal 0. They're not part of the blocks that are moving or the masses that we're interested in. I think it may have even said in the problem that the pulley's, weight is negligible. So all we're doing is we're just showing the forces that are acting on it. So here we have a negative T2 and we've got a positive 2T1, right? Equal to 0. So if we, move to the other side, I like keeping the single variable on the left. I have a negative T2 is going to be equal to a negative 2T1, right? Both become positive, all right? I still have two unknowns in this equation. So I've got a third equation now. And how many unknowns do I have? I've got A and AB. So that's 2, 3, okay, 4, and I've got 3 equations. So 1, 2, 3, 4 variables, and I only have 3 equations. But I do know a relationship, okay? As I look at this pulley setup, okay, you're going to notice that when I move A, B is not going to move at the same rate, okay? So for instance, when this cord is going down and around, okay, when that cord is going down and around, the distance that B moves is only going to be half as much as what A moves. So I'm going to have to move A further, and then B is going to go up. I am certain that in your physics classes that you guys did experiments with pulleys and probably had different pulley arrangements, okay? And this is one of those cases where this is not a one-to-one. If this wasn't wrapped around here, it would be a 1-to-1. Okay, so if this was just attached right to block B, however far block A would go, block B would go. But because we have it around the pulley here, all right, what it does for us is as we pull on A, we have to pull A further along, and then B is going to come up slower. And because there are two strings that are attached here, the distance relationship, okay, so I'm going to call this distance relationship is going to be, now, even though we have two directions that we're pulling, we're just going to call it X as a distance. So I'm going to say XB is equal to 1/2 XA. This is just distances. The book uses X. I would have probably used distance instead of X, but I'm just being consistent with the example. So it's truly how far is B moving? Yes, B is moving in a Y direction, and in relationship to how far A is moving. A is in an X direction, but they just kind of kept it consistent. Now, this doesn't really help us because we're interested in, remember, we're trying to find accelerations, right? We're trying to find accelerations. So we do know that if we take two derivative levels, if you would, of the distance, we can get to acceleration. Okay, we did that in our last module. So we can say that dxb over dt is going to be equal to 1/2 dxa over dt. This is velocity, right? So we can say velocity of B is equal to 1/2 the velocity of A. And we can do that one more time. So this is one derivative, and we're going to do it another time. So we can say, oh, dvb dt is equal to 1/2 dva over dt. And if we take velocity divided by time, what do we get? Get acceleration. So this is going to be the acceleration of B is equal to 1/2 the acceleration of A. Okay. So we did two derivatives, if you would, to get to the acceleration equation. Okay. Everybody see and understand that? Makes sense? All right. So now we have 4 unknown variables, but we have 4 equations. We have our relationship of our accelerations, the relationship here of our tensions, and then we have the previous 2 based on the kinetic and the statics. Okay, so we have 4 equations with 4 unknowns, right? So what I'm going to do is, now if you don't have to do this, but just so that on the paper here they're organized, I'm going to say, I'm just going to rewrite my equation number 1 was T1 is equal to 100 times the acceleration of A. My equation number 2 was T2. I don't know if I want to change. I'm going to leave it in the same form. We could do T2 is equal to, but I'm just going to leave it in the same form that it is here. 2940 is equal to negative 300 times acceleration of B. Equation number 3 is from the pulleys. T2 is equal to 2 times T1. And then the last equation that we did here, which was for the distances, this is the acceleration of B is equal to 0.5, the acceleration of A, or 1/2. Okay. So now we can just do, if you would, substitution to try to solve for things. So sometimes it takes a little bit of trial and error. I'll tell you what I did. So I'm going to substitute number 4 into number 2. And again, I know you guys could do this. It would just probably be a little bit of, figuring out here, but I'm kind of saving a little time here. So, so that means I'm going to substitute number 4. So number 4 for the AB, I'm going to put in 1/2 acceleration of A up in here. Okay. So I'm going to rewrite that T2 minus 2940 is equal to negative 300 times 0.5 acceleration of A. So expanding this out, multiplying these two, I'm going to get T2 minus 2940 is equal to minus 150, 1/2 of 300 times the acceleration of A. Didn't get much further, but I'm going to substitute number 1 into number 3, all right? So looking at number 1 here, I've got T1 is equal to 100 acceleration of A. I'm going to go down here and I'm going to take my 100 acceleration of A and put it in for T1, okay? So I've got T2, so into number 3, T2 is equal to 2 times, this is where my T1 is. So now I'm going to multiply that by, so T1 is equal to 100 acceleration of A. Okay. Oh, look what I've got here. 2 equations with the same 2 unknowns. Okay. Well, let me expand this out. T2 is equal to 200 acceleration of A. Now I can take my 200, right? Acceleration of A, and I can put it right in there. And then I'll have an equation with all the same unknown, or just one unknown, I should say. So I'm going to rewrite that. Sorry, not T2. I want to put 200 acceleration A minus 2940 is equal to negative 150 acceleration of A. So I only have one unknown now. Okay. So now I'm going to take this 150. I'm going to add it on the other side. I'm going to take the 2940 and put it over there. So I'm going to do that in this next step. So this is going to be 350 acceleration of A is equal to 2940. Okay. Dividing both sides by 350. Acceleration of A is going to be 8.4 meters per second squared. So good. I'm going to give you a second to catch up to that. All right. So here, and then substituting back in. This is our T2. All right. I'm not seeing anything in the chat box, so hopefully that all makes sense. So now that is our acceleration of A. All right. Now we've got one of them solved for. So now it's just a matter of substituting that value back in to get the next value. So as you recall, we need to find the acceleration of A and B, and then T1 and T2. So to get the acceleration of B, I'm simply going to use the equation number 4 here, substituting in our value of 8.4 for that acceleration of A. So we've got AB is equal to 0.5 times 8.4 meters per second squared. So that was the acceleration of A. So our acceleration of B is going to be 4.2 meters per second squared. Remember to put your units on your final answers, and this certainly is a final answer. Okay. So they magically appear. If you want to put them throughout, you certainly may. But like I said, just be careful with knowns and unknowns. Then the last two that we need to do is going to be our T1 and our T2. So we look back at our equations. We're going to find T1 by using our acceleration of A. So we're going to go back to that equation number 1. So T1 is going to be equal to 100 times 8.4. Okay. So T1 is 840 newtons. Okay. And then T2 is going to be equal to 2 times T1. We just solve for T1. So T2 is equal to 2 times T1, or 840. So T2 is going to be 1680 newtons. All right. Does anybody need to see any parts of that at all? It's a little harder for me to pace when I don't have people in the classroom. Okay, I'm not getting a
Can you
request.
show me the first page?
Yes, I absolutely can. So here's the first page.
Yeah, mainly the top part.
The top
I just
part
missed
here.
that when we started.
So that is our second sample problem. Now, the next sample problem that we're going to do a little bit further along, and it's the last sample problem that we'll do in this chapter as well. This is the last sample problem we're going to do is going to be sample problem 12.6. So if you wanted to open up to page 737, you will find the problem statement there. Christian, did you get what you needed?
Yeah.
Okay, all right. So any other questions on sample problem 12.3 before we move on to our last sample problem? Okay, not saying anything, so no news is good news. If so, just let me know, and I always can come back to this as well. So I'll keep this on the side here. Okay, so let's go back to our PowerPoint. And we already did this problem. So now we're going to be looking at items that are rotating about a fixed center. And as we know, the acceleration then is going to have two components. It's going to have a normal and a tangential component. And we saw this in chapter 11 or in module 1. But when we look in terms of Newton's second law, we can say that the summation of the forces is going to be equal to mass times acceleration. But now we're going to have two sides of the acceleration, or two components of the acceleration. The normal, which is always going to go from the point that we're looking at, and it's going to point towards the center of rotation. And then the tangential is always going to be perpendicular to that normal force in the direction of acceleration. So remember, it's important that you know, if you would, that if it is slowing down, the acceleration is going to go in the opposite direction of the velocity. If it is speeding up, on the other hand, it'll go in the same direction as the velocity, okay, that tangential. So you can see here that we have the forces, the normal and tangential, and then we have the mass and the acceleration, normal and tangential. So this is going to be the type of diagrams that we look at. One on the left-hand side for the forces and the one on the right-hand side for the inertia terms, or the movement. Right. Now, additionally, they expanded out the tangential and the normals on how you would find each one of those values. If you recall from chapter 11 or module number 1, I'm going to go underneath here towards, I think it was the last section that we looked at, the equations for calculating or determining the actual magnitude of the tangential component of acceleration is going to be the change in velocity over the change in time. And then the normal is going to be the velocity squared divided by, and this is going to be that radius of rotation, or in the case of the example that we're going to be looking at, it's going to be the radius back to the center of rotation, okay? I think we were looking at it in terms of curvature the last time, like when we had a trajectory, okay? So, so those are going to come back in handy for us. So if I go here, sample 12.6 is going to be the problem that we look at, sample problem 12.6. So here we have a bob. So it's really just this ball on the end of this cord. Has a 2 millimeter distance, a radius here. Pendulum is described as an arc of a circle in a vertical plane. If the tension in the cord is 2.5 times the weight of the bob for the position that we see right here, find the velocity and the acceleration of the bob at this position. Okay, so they're giving it to us at 30 degrees, the 2 meters, and then here's the mass itself. Okay, so what we're going to do here is, as it says, we're gonna resolve the equation for the motion. We're going to solve for the components of the normal and tangential accelerations, and then we're going to solve for the velocities and such. Now, let's go underneath and kind of draw what we need to draw. So first of all, okay, this is sample problem 12.6. Okay. We know that the tension in that cord, and we'll draw the tension as a force in just a little bit, 12.5 times the weight. We're going to expand the weight out to be mass times gravity. So it's that full quantity, okay? We also know that the radius to the center of rotation is 2 meters, okay? We're not given the mass of this. We're going to find that we don't need it. What we want to find, okay, is going to be the velocity of that bob, as they're calling it, okay? And the acceleration, okay? The total acceleration. Okay. Now, I had started working this because when I looked at it, I was like, oh, well, of course. We're going to put it in X and Y components and go through the problem. And I noticed that the book didn't set it up that way at first. And I'm like, I'm just going to do it the way that I normally do. And it became kind of a logistics nightmare, meaning I had X and Y components for every single thing along here. And what the book did, and I should have done it right away, but I came around to their way of thinking, is they tipped the axis system to go along with or align with that direction. So I'm going to show you how to construct this. So it's a little bit, I think it's easier. The book was right. The book was right in this case. So, so I'm going to start over here. The diagram towards the left is going to be my, my statics diagram, if you would. This is going to be the center. And then I'm going to grab my protractor that I'm now seeing. And we are going to just tip this at that 30-degree angle, okay? And then 90 degrees to that, I have this, okay? So this is the center of my bob. Draw a circle around it, okay? This is going to be what we're gonna call the N axis, and this is going to be the T, the normal and tangential axes, okay? Now, this is the string going up to that center of rotation, and this is the bob. So the tension that string sees, okay, is going to be along that cord, pulling away from the bob. So this is T is equal to 2.5 mg. Okay. So if I would go like this is like the Y direction, right? But we're going to keep it at an angle. All right. So we're just like tilting our axis system and giving it different variables just so it's really not an X and a Y anymore because it is tilted. Okay. Then going straight down, again, this is the force, its weight, going straight down is going to be the weight is equal to M times G. Okay. And the angle that we see here is 30 degrees. So this is the static side. This is the sum of the forces, all right? It's going to be equal to, now we're going to do that very same thing. So I'm going to kind of go straight across. All right, this is my bob. And I'm going to draw parallel that same axis system going through and perpendicular. Okay, so this is our T, this is our N. Now over here on the right-hand side, the inertia terms are going to be, now this is from the center of rotation and pointing, I'm sorry, it's from the center of the bob pointing towards the center of rotation. This is going to be the mass times the normal acceleration component of the acceleration. And then in this direction, because remember, this is kind of coming down, it's a pendulum, it's kind of coming down this way. Along this T axis, this is going to be perpendicular to that, the mass of that bob times the acceleration or the tangential acceleration component. Now, as we look here, because we don't have an X and Y here, we have to name our convention a little bit differently. We have to say N and T, and this is the positive, okay? Because then our positives and negatives are going to go along with this convention. So up is going to be positive, and if you would, down and to the left is going to be positive. Okay. Questions so far? All right. Now, we're going to first look at this by summing our forces along that t-axis, okay? And then we're going to sum our forces along the n-axis or the normal axis. So I'm going to kind of divide this in half, if you would, and do this on either side. So this is going to be sum the forces along the t-axis or tangential axis equal to mass times the acceleration t. So it's kind of looking at this one and this one, all right? Now, on this side, we would see, if you would, a force along that t-axis right here as a component of the weight, right? So this would be m times g along that t-axis, right? So just looking in that direction. Now, to get that, we know that this is 30 degrees, right? And technically, this is going to be an equivalent length. It would be the side opposite is going to be equal to that value in terms of the mass and gravity. So we're going to call that force out as m times g times the sine of 30 degrees. Or you could do 30 or sine of 30 times m times g. Okay, so this is the weight, which is really that what's going down here. It's expanded out. And we're just trying to find the t component, if you would, and that would be equal to, so this is mgt. Okay, now this is pointing down and to the left, and according to our convention, that's the positive direction. Okay, so we're going to leave that as a positive value, right? That's the only force on this side. Okay, that's the only force on this side, and we're going to set that equal to the mass times the tangential acceleration. Okay. Now, what I'm going to do is I'm going to find the decimal equivalent of 30 sine, and that's going to be 0.5 times m times g is equal to m times the tangential component. As you look on either side here, do you see anything that we can cancel? The mass. The mass. The g stays. So we know that the g is 9.81. So this is going to be 0.5 times 9.81, because that's the gravity. It's going to be equal to our tangential component of the acceleration. So multiplying that together, we're going to get 4.905 meters per second squared is equal to the tangential. Well, we don't have, you can put it in. We're going to put a little cloud around this. This is a component of the acceleration, and we need to find the acceleration. So I put the units there. It's fine. We're going to be using Pythagorean's theorem in a little bit to get the full acceleration. Okay, so any questions on the tangential component so far? Okay. Now to get the normal component, you'll notice that the normal component of the acceleration is along the n-axis. So now we're going to sum our forces along that n-axis. And as you can see here as well, there is going to be an n component of the weight. So this is going to be mg normal component, right? So if we sum our forces along the normal axis times, it's going to be equal to the mass times the acceleration normal. Now we're going to look along this line right here, okay? This line right here. So we know that we have a positive tension, which is equal to 2.5 times the weight or mass times gravity. So we're going to put that over here. Now that's in a positive direction. So that is going to be 2.5 mg, okay? Minus, so this is T if you would, right? Make it like this. This is T. Minus, going down, this is going to be, this time, the cosine, because it's the side adjacent to the 30. So cosine 30 times mg is going to be the mg normal component, right? It's going to be equal to then mass times the normal acceleration of gravity, okay? So as we look here, this is going to be 2.5 mg minus 0.866 mg is equal to m times the acceleration normal component. We can factor out m and g, right? So we can pull out mg here, and this is going to be 2.5 minus 0.866 on the inside, okay, is equal to m times the normal acceleration. And we can see here again, the mass cancels out on either side, right? So now we know that our gravity is going to be equal to 9.81. So we can distribute that on either side here. So we're going to get 24.525 minus 8.4955 is equal to the normal component of the acceleration, or 16.03 meters per second squared equals that normal component of the acceleration. Any questions there? You guys are quiet tonight. I don't know what it is. Okay, so we've got our normal and our tangential. Now, I was disappointed because the book stopped there because they asked for the acceleration. So we're going to go a step further and we're going to get the total acceleration, okay? The total acceleration, as we know, is going to be the resultant of those two forces, right? So, I mean, you could draw it here if you wanted to, but basically what that's going to be is it's going to be, we're going to take the normal and tangential, and we're going to use Pythagorean's theorem to find the total acceleration. So we'll kind of go like this. So we know that acceleration is going to be equal to the square root of the normal squared plus the tangential component squared. So that is going to be the square root of 16.03, not going to put the units in, plus 4.905 squared, right? So your total acceleration is going to be 16.8 meters per second squared. And this would be the final answer. Again, the sample problem in the book stopped short of that for some reason, even though they asked for it, but we're solving it as far as part of our sample problem. All right, and then the very last thing they wanted us, so we now have the acceleration, we found that 16.8 meters per second squared. Now we need to find what the velocity is of that bob, okay? Now, if we go back to our chapter 11, our velocity can be found easily by using that normal component and the radius of rotation, okay? And we were given the radius of rotation was 2 meters. So I actually have to go to the next sheet here. And I know that it's going to use that same base equation. The normal acceleration is going to be equal to the velocity squared divided by that radius of rotation. So we're gonna rearrange that. We're gonna say v is equal to the square root of, because it's v squared, the normal acceleration times that radius of rotation or radius of curvature. So we know that our normal acceleration we calculated to be 16.03, okay, times that radius of rotation is 2, okay? So our velocity is going to be equal to 5.66, and our units would be meters per second. Any questions on that? And that takes care of the things that we needed to solve for. So we need to solve for the velocity, which we just did, and the total acceleration. And remember, total acceleration, we're adding this. The sample problem did not. Okay. So any questions at all on this last sample problem that we're looking at? Okay. All right. If not, then that is that concludes, if you would, the 3 practice problems that we have from chapter 12. Okay, from this section of the module. We will be moving on to chapter 16 the next time that we're together. Now, if we go back to our PowerPoint here, this was the problem we just worked through. Like it says here, this concludes chapter 12. We are now ready to work. I have 3 application problems in the module 2 application problems that are not from the book. So we're going to take a peek there first. You would be ready to solve these 3. So you could start working on these, you know, this evening or before the next time that we're together. So if I go back here and I exit out of my PowerPoint, and I go to my applications, module 2 application problems, you will find that in the application problems, I have app 1, app 2, and app 3. These are not from the book, all right? These are based on the 3 sample problems that we did. Unfortunately, I didn't find any in the book that I liked that I felt like went along nicely with the sample problems that I picked, which are going to be helpful for later on. So instead, what I did was, for the first one here, it says using sample problem 12.1, which was the first one that we went over tonight. It's found on page 731 in your book. Find the acceleration this time of the block, noting the following changes. This time, I'm giving you the value of P, what the block actually is, and I'm changing the angle to 40 degrees. So if we recall, sample problem 12.1, hold on. Sample problem 12.1. Underneath my camera here. So what I'm referring to here is we want to find the acceleration this time. It was given in the last problem. Last time when we needed to solve for P, but this time I'm giving you P, and instead of the 40 degrees, it's going to be, I'm sorry, instead of the 30 degrees, it's going to be 40 degrees. So you want to replace that 30 degrees. I'm also telling you that the block this time weighs 150 pounds. Last time it was 200. And I changed the coefficient of friction. And then here's the final answer that you should get. Okay, so I kind of made up my own problem. It's not exactly like the one for sample 12.1, but it's a variation on it, solving for a different variable. Okay, so that'll be the first one that you can work on pertaining to what we did tonight. The second one is going to be the second application problem, and this one is pretty much using 12.3 exactly the way it's at. I just changed the masses of each one of the blocks. And then what you want to do is you want to find those accelerations and the tensions, kind of going through that same process again. And then the third problem is going to be based on sample problem 12.6, the one that we just went over. You want to find the total acceleration of the bob to maintain a velocity this time of 8 meters per second, noting the following changes. I'm changing the bob to 4 meters long. The angle is going to go to 45, the one that was 30. And then the tension in the bob is going to be 2 times the mass times the gravity. And then this would be your final acceleration, final total acceleration for that problem. So this one too is very similar, but a little bit different. So make sure that you note the changes that I made there. Okay. So, so that is actually what I wanted to go over this evening. So I am going to stop sharing and I'm just gonna I'm gonna check. So funny. What if we did it our way with components? What? Oh, which you mean like that last problem that we just looked at, Lex?
Yeah, like what if we use like your
Try
X and
it.
Y?
Go ahead. You know what? I went the component method too. Like I started out that way. And you know what? It just got like everything had components and I started getting a little like, oh my gosh, I don't and I kind of gave up and I glanced at the book. I'm like, how come you're only doing this in like two steps? And it was because they tilted it. So I found that was actually easier. But go ahead and try it, Lex. And yes, you'll be able to solve it. It'll come up with the same answer. It's just going to be, yes, you're just going to have a little bit more trig, a lot more trig. Yeah. And then what if we did it your way with, okay, that was that one. You get X and Y component for everything. You can do it. It's just a lot. Yeah, absolutely. And many tiers. Nice. Could you show the pulley diagram for a second too? Absolutely. Oh, I'm still recording. Let me peek, but let me just let me go back to over here. Oopsie. Over here, over here, over here. Still recording.